You're being pulled through space right now at over 600 kilometers per second. Not just you. Your house, our planet, our solar system, and galaxy are all moving towards something astronomers call the Great Attractor. Like an invisible cosmic whirlpool, this gravitational anomaly is so massive, it affects 100,000 galaxies across a region of space, 500 million light-years wide. The most unsettling part? We can't clearly see what's pulling us. The Great Attractor sits behind the dusty plane of our own galaxy in what astronomers call the zone of avoidance, a cosmic blind spot. Something with the gravitational force of tens of thousands of galaxies is actively pulling everything you know toward it, hiding just beyond our ability to observe it directly. Picture this, a cosmic detective story that begins in 1973. While most astronomers were focused on the universe's expansion following the Big Bang, two scientists at Australia's Parkes Observatory noticed something peculiar. Galaxies weren't just moving away from each other. They were being pulled sideways across the cosmos at astonishing speeds. R.B. Tully and J.R. Fisher, working with radio telescopes that could see beyond what optical instruments revealed, had stumbled upon something that would challenge our understanding of cosmic structure. These cosmic sleuths discovered a gravitational anomaly of staggering proportions. Galaxies throughout our cosmic neighborhood were being drawn toward a specific region of space, at velocities reaching 700 kilometers per second. Speeds so extreme that conventional cosmic structures couldn't explain such gravitational influence. It was as if someone had placed an invisible cosmic magnet in deep space, and thousands of galaxies, including our Milky Way, appeared to be powerless against its pull. The investigation gained momentum when scientists detected subtle temperature variations in the cosmic microwave background radiation. One side of our galaxy appeared slightly warmer than the opposite, a temperature difference of less than 1/100th of a degree Fahrenheit. This minuscule gradient revealed something profound. Our entire galaxy was rushing through space toward an unseen destination. Think of it like this. When you stick your hand out of a car window while driving, you can feel the air resistance even with your eyes closed. Similarly, as our galaxy moves through space, it creates a subtle wind effect against the cosmic background radiation. Warmer in the direction we're moving toward, cooler in the direction we're moving away from. This extraordinarily sensitive measurement confirmed our galaxy's directional movement with remarkable accuracy. What made Tully and Fisher's work so groundbreaking was their demonstration that this wasn't an isolated phenomenon affecting just the Milky Way. Their observations mapped hundreds of galaxies being pulled in the same direction, outlining the contours of an invisible gravitational behemoth lurking in the darkness of space. The scientific community faced a genuine puzzle. Calculations from the late 1970s and early 1980s indicated that whatever caused this cosmic migration would need mass equivalent to tens of thousands of galaxies, concentrated in a relatively small cosmic volume. By 1986, astronomers had triangulated the approximate location of this gravitational anomaly, somewhere between 150 and 250 million light-years from Earth, in the direction of the constellations Triangulum Australe and Norma. Yet telescopes revealed nothing substantial enough to explain the measured gravitational effects. In 1987, astronomer Alan Dressler named this cosmic enigma the Great Attractor. This force was reshaping the movement of approximately 100,000 galaxies across a region spanning over 500 million light-years. This discovery fundamentally transformed our understanding of cosmic motion. Before these observations, astronomers primarily viewed galaxies as moving away from each other due to the universe's expansion. The Great Attractor revealed a complex cosmic dance where galaxies both expand outward and simultaneously flow toward massive gravitational wells, a gravitational network later recognized as the cosmic web. The identification of the Great Attractor also exposed a humbling truth about our cosmic perspective. Despite advanced technology and scientific progress, fundamental aspects of our universe remain hidden from direct observation. Here was a force powerful enough to redirect our entire galaxy at 600,000 miles per hour, yet we couldn't directly see what was causing it. This astronomical blind spot isn't just a minor inconvenience for scientists. It's perhaps the greatest cosmic curtain ever drawn across our view of the universe. When astronomers finally pinpointed the approximate location of the Great Attractor, they faced a problem more frustrating than its massive scale. It sits directly behind the densest part of our own galaxy. Imagine discovering that the answer to one of astronomy's greatest mysteries lies in the one direction where your telescope simply cannot see. The zone of avoidance represents an astronomical blind spot so significant that it conceals approximately 20% of the observable universe from our view. This critical band stretches across our night sky, created by the Milky Way's galactic plane. With its dense concentration of stars, gas, and cosmic dust, our home galaxy effectively blocks everything behind it, creating a cosmic shadow zone where countless galaxies remain hidden from conventional observation. The problem stems directly from our position in the cosmos. Our solar system sits embedded within one of the Milky Way's spiral arms, placing us inside the very disk that creates this observational challenge. When we look toward the center of our galaxy, we're attempting to peer through an impenetrable cosmic fog. The interstellar dust absorbs visible light with such remarkable efficiency that it diminishes the brightness of objects behind it by factors of billions, rendering conventional optical telescopes essentially useless for studying anything beyond this veil. What makes this particularly frustrating for astronomers is the cosmic irony at play. The Great Attractor, massive enough to influence thousands of galaxies, sits squarely behind this cosmic curtain. It's as if the universe placed the most intriguing gravitational puzzle in our cosmic neighborhood, precisely where we struggle most to observe. The Great Attractor remains hidden not because of its distance or faintness, but because our own galaxy blocks our view, like trying to see through a wall that we ourselves built. Science, however, has developed ingenious workarounds to peer through this cosmic fog. When visible light telescopes reach their limits, astronomers turn to wavelengths that can penetrate the dust, primarily X-rays, radio waves, and infrared radiation. These alternative methods have revealed fascinating structures, including the Norma cluster, a massive galaxy cluster approximately 220 million light-years away that appears to sit at the heart of the Great Attractor region. This cluster contains numerous large old galaxies, many colliding with neighbors and radiating significant radio waves, evidence of powerful gravitational interactions. The investigation is further complicated by distance. At 150 to 250 million light-years away, we're studying the Great Attractor as it existed when dinosaurs roamed Earth. The light has traveled toward us for hundreds of millions of years, making our observations inherently historical. Even the remarkable Hubble Space Telescope can't fully overcome this obstacle, as the Milky Way's dust and gas continue to obscure many objects behind it, necessitating continued reliance on infrared and radio observations. Consider the implications of this astronomical blind spot for all our technological advancement and scientific progress. We still cannot directly observe one of the most powerful forces affecting our galaxy's journey through space. It stands as a humbling reminder of our limitations, that despite our best efforts, significant parts of the universe remain hidden from view, not because they're too distant, but because our cosmic home itself blocks our line of sight. Just as we've resigned ourselves to the limitations of our cosmic vantage point, the mystery deepens beyond mere visibility problems. If the Great Attractor contains only 1/10 the mass required to create its observed gravitational effects, what unseen force is actually controlling the motion of 100,000 galaxies, including our own? The answer might force us to rewrite the fundamental laws of physics. The story of the Great Attractor grows more complex with each new observation. While earlier theories pointed to a massive concentration of galaxies exerting gravitational influence, recent discoveries reveal a more intricate picture. The Great Attractor appears to be merely one component of the much larger Laniakea supercluster, a cosmic structure encompassing approximately 100,000 galaxies across 500 million light-years of space, all flowing toward a common gravitational center. This expanded view still presents a fundamental paradox. The 2005 clusters in the Zone of Avoidance project delivered a startling revelation. The Great Attractor possesses approximately 1/10 of the mass scientists initially calculated. This dramatic discrepancy raises profound questions about what's actually pulling us through space. The visible matter simply cannot account for the gravitational effects we're measuring. Our cosmic neighborhood contains additional players in this gravitational drama. The Shapley supercluster, located beyond the Great Attractor, represents one of the largest known concentrations of galaxies in the observable universe. Its immense mass likely contributes additional gravitational effects that compound the pull we attribute to the Great Attractor. What we observe resembles a cosmic chess match where massive structures exert competing influences, with our galaxy caught in the strategic crossfire. This mass discrepancy has prompted several theoretical explanations. Dark matter, the mysterious substance comprising roughly 85% of the universe's mass, yet remaining invisible to our instruments, likely plays a central role. Substantial dark matter concentrations within the Great Attractor region could amplify its gravitational influence far beyond what its visible matter would predict. This would explain how a structure with apparently insufficient mass exerts such powerful effects across vast cosmic distances. The Great Attractor serves as a natural laboratory for testing fundamental physics. Some scientists question whether our gravitational models, which work perfectly at smaller scales, break down across supercluster distances. More exotic theories propose massive primordial black holes. Theoretical black holes formed in the earliest moments after the Big Bang, lurking in this region. Others suggest space-time distortions creating gravitational effects without corresponding mass. When we look at this cosmic puzzle, are we witnessing the limitations of our physics or merely the limits of our observation? Adding another dimension to this gravitational landscape is the dipole repeller, essentially the opposite of an attractor. This region appears to push galaxies away rather than pulling them in. Our galaxy navigates these conflicting gravitational currents, pulled forward by the Great Attractor and Shapley supercluster, while simultaneously pushed away from the dipole repeller's vast cosmic void. Current and future research projects, including the ambitious Square Kilometre Array, aim to pierce through our galaxy's dusty veil and map these structures with unprecedented precision. These observations will help determine the true distribution of matter, both visible and dark, and potentially reveal whether our understanding of gravitational physics requires fundamental revision. The quest to understand the Great Attractor isn't ending, it's evolving. Like any good detective story, each clue reveals new mysteries. The Square Kilometre Array represents our next leap forward, promising unprecedented clarity as we peer through the cosmic dust obscuring our view. Our cosmic investigation continues as astronomers study cold spots in the cosmic microwave background radiation, temperature variations that reveal the Great Attractor's gravitational footprint across space-time. These subtle imprints demonstrate how this massive structure reshapes our universe at its grandest scales. The Great Attractor stands as a monument to cosmic uncertainty, a gravitational enigma influencing our galactic neighborhood while evading complete understanding. As we build more powerful instruments, what fundamental principles of physics might be rewritten by what lurks just beyond our current vision? Until next time, thank you for watching. Don't forget to like and subscribe.